which is theorized to begin at around 250 kilometers. While most of our atmosphere is composed of nitrogen, the upper region of our ionosphere is home to lighter elements like oxygen, hydrogen, and helium. When photons from the sun collide with these elements in the upper atmosphere, they can knock electrons loose from the elements in a process called ionization, leaving positively charged particles called ions and negatively charged electrons. Because of the opposite charges of the negative electrons and positive ions, they are attracted to each other and become tethered together by an electric field. It's this electric field that constitutes a major part of the ambipolar field. The electrons within the electric field are so light that the slightest push could send them flying out to space, while the ions are more than 1,800 times heavier than the electrons and sink toward the ground due to gravity. The subatomic tug of war works in both directions, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. This outward pressure of ionospheric electrons is what creates the ambipolar field, depicted here as the sparkling blue glow around our planet. The upward lift inflates our planet's ionosphere and accelerates some ions enough to escape from the atmosphere, creating the polar wind along our poles' magnetic field lines. What's more, the ambipolar field can achieve this acceleration of plasmas without heating them, providing an explanation for the cold plasma scientists had detected escaping from the ionosphere. It's the bidirectional nature of the interaction between ions and electrons that gives the ambipolar field its name. The Latin prefix ambi means both, and polar refers to the polar regions, where the electric field's effects are felt the strongest. Collinson, the Endurance mission's primary investigator, called the ambipolar field an agent of chaos, stripping particles from our atmosphere away into space. Hydrogen ions make up the majority of the polar wind. They are so light, the ambipolar field's upward force of these electron ions is 10.6 times stronger than the force of gravity, leading the ions to accelerate up at supersonic speeds and escape from our atmosphere above the Earth's magnetic poles. Scientists have found that our planet loses about 3 kilograms of hydrogen gas every second, or 95,000 tons per year. Additionally, the Earth also loses about 50 grams of helium per second, or 1,600 tons of helium gas per year. A smaller but still measurable amount, and a much smaller amount of other gases like oxygen. However, not all of this is due to polar winds. It occurs through a combination of factors, including thermal escape and non-thermal escape mechanisms such as polar wind. But don't worry. Despite our planet losing several thousand tons of its atmosphere to space every day, we are nowhere near running out of air. The planet won't run out of oxygen for 1 billion years. It will be another 1 billion years after that before our oceans will have been depleted of most of their hydrogen. Around 4 billion years from now, our planet may look very similar to how Venus looks now. All of our water will have evaporated, and the greenhouse effect will have become strong enough to melt rock, leaving our planet a dry, lifeless world. Keep in mind that modern humans have only existed on this planet for around 300,000 years. Our species would need to exist more than 3,300 times that length to be around in 1 billion years. While not really important